What is my chalkboard doing? Making weird noises. This is really weird. It's to make lower in series expansion. So meaning, I'm literally shaking right now. What the Whew, holy crap. Okay. A huge thanks to my Patreon supporters for making this episode possible. Good morning, fellow mathematicians, welcome back to another video. So for some odd reason that I can't really explain, one of my most recent videos, the one where I derive the pendulum's equation solution using nut approximations video, gained quite some attention, which I am really glad it does because, well, it gets me some subscribers. By the way, if you're not subscribed yet, most people are not, see the statistic right here, then make sure to subscribe to the channel. It's for completely free, alright, and you can always unsubscribe if you don't enjoy the content anymore. But yeah, I want to follow up on this video a tiny little bit more because the complete elliptic integrator of the first kind popped up at the very end, and it's kind of useless to most people. Okay, it's just some integral representation, non-elementary thing. And yeah, we would like to derive a series expansion for this boy right here today, which is one of my most favorite series expansions ever. It's kind of not too hard to derive, and it just looks pretty fancy, gives us some very nice approximations if you truncate it pretty early. And yeah, later on the advent calendar we are also going to implement a Python script spitting out values for the complete elliptic integrator of the first kind in the process. So that's going to be quite cool. But before we dive into the main video, I would like to thank today's sponsor, The Rich, for once again sponsoring a video here on this channel. Let me tell you one thing, love this tiny little thing, as well as their absolutely fabulous backpacks. Oh, those are just great, looking so good, and they are weatherproof, by the way. So short and spicy introduction about The Rich. The Rich is basically producing very high quality lifestyle products, for example those backpacks, or their flagship products, their wallets. Next to them looking extremely good. Just look at it. It's extremely sleek. You can put a lot of cards into here up until 12, and also you have a money strap at the back or clip. They also come in various colors, including their newest collection, which comes with the damask color, and it just looks absolutely amazing. I just think that the style of this thing is so cool, and I'm going to get myself one of the damask ones because seriously, just looks so freaking cool. But other than that, the biggest promise they give you on this wallet right here is on its durability. You are going to get a lifetime warranty coming with this wallet. It's never going to break, and if it does in any way, if something is going to tear apart, then you can throw it back their way and they are going to give you a replacement product, or you are going to get a full refund plus also your shipping refunded. So that's a really good deal if you ask me. And I am using their products for quite a while now, for a few months by now, especially their backpacks, and they are just so high quality. They just look good and they just do their thing. And if you don't trust me on that, make sure to check out their over 30k 5-star reviews all over the place. Amazon, Google, and even their website. They are going to tell you the same thing. Does what it has to do and even better, and it looks good, and it's going to change your pocket situation completely. Okay, you don't need your old wallet anymore once you get the Rich wallet. So if you want to try it out, if you think that that's something that you could benefit from, then make sure to check out the link at the top of the description, rich.com/papaflammy, or just use the code papaflammy at checkout. You're going to get 10% off your whole order, as well as worldwide free shipping. So that's an absolutely great deal, and now we are going to dive right in, and as always I'm going to throw my Rich wallet away because yeah, it can handle that actually. So I'm going to go through the process of deriving the series representation step by step. I could make use of some prerequisites, which we could definitely do, but I would like to derive this from scratch because it's actually not that hard. And before we get into the main game, I would like to concentrate on the integrand a tiny little bit, because the integrand is actually a function of the form 1 over square root of 1 minus x in some way, okay? And if everything is in the radius of convergence, we can plug x squared into there, so make a substitution, x goes to x squared, or rather k squared times sine squared of theta, and hence we can turn this into a Taylor series expansion, which we are going to do really quick. It really doesn't take too long, and if you're asking yourself where you can get this wall tapestry from, Stamford, you know this by now probably. What is my chalkboard doing? Making weird noises. This is really weird. So we are going to take a look at the function 1 over square root of 1 minus x, which is the same as f of x being equal to 1 minus x to the negative 1/2 power. And as always with with Maclaurin or Taylor series expansions, we are going to differentiate this a bunch of times and see if we can support a certain pattern. So let us differentiate this once. So f gram of x is going to be okay, tracking the -1/2 down. Then we are going to multiply it by this part just with the exponent reduced by 1. So -1/2 minus 1 is -1.5 is -3/2. Multiplying it with the inner derivative, which is -1, we are going to get rid of negative sign that we tracked to the front initially. So this right here is the derivative. We are going to compute second derivative now. Okay, what's the second derivative? I mean, it's going to be the same process. We are going to keep the factor of 1/2 right here. Also, we are going to track the -3/2 down. Also, we are going to multiply it by 1 minus x tutor, reducing the power by 1, -5/2, inner derivative -1, getting rid of negative sign here, okay? Process is going to continue. So f triple prime of x is going to be keeping the constant, 1/2, 3/2, and then 5/2, tracking this down, negative is going to cancel out in the process, 1 minus x tutor, and then we are going to get -7/2, and that's basically it. And the process is going to continue indefinitely, okay? Infinitely many times, but we can actually find a formula for the cave term, and it's actually pretty easy to find out. So at first I would like to spot a few patterns here at first. You might notice at first that the 1 minus x factor is going to be preserved all the time. But what is the power on the 1 minus x factor? So the cave derivative with respect to x is going to be, okay, 1 minus x is going to stay here, but what with the power? I mean, it's always a negative sign. Okay, 7. This has been the third derivative, and now we are going to get 7 out here. How can you get 7 exactly? That's quite curious. I mean, you can get 7 from 3 if you take 2 times 3 plus 1. I mean, this right here is the odd decomposition of 7. Does this hold for the other ones? I mean, 2, okay, 2 times 2 is 4 plus 1 is going to give us 5. Oh, that's pretty cool. So 2k plus 1/2. This right here is our power. Also, what are we having here? I mean, on the third derivative, we are going to have 1 times 3 times 5. We have covered this before. This is nothing but 5 double factorial. Do we have same situation here? So on the second derivative, 1 times 3, this by definition is 3 double factorial, 1 double factorial, and something up here. We are going to talk about this later. So we are going to get some kind of double factorial up here. Double factorials are actually really useful in the context of this function, for example. Hence, we are going to make use of it. If you don't know what it is, take a look at Wikipedia, for example, or some other videos I have produced not too long ago, actually. So, okay, we are going to get 5 double factorial here, 3 double factorial, but this has been on the third derivative and this on the second derivative. How can we get 5 from 3? I mean, we can either add 2 to 3, but this doesn't make sense with this one. So adding 2 to 2 gives us 4, doesn't make any sense. But maybe we can go the same way with the odd decomposition here. I mean, 5 is nothing but 2 times 3 minus 1. Okay, does this hold for 3? I mean, 2 times 2 is 4, minus 1 is 3. Hey, this is pretty good. So meaning overall, we are going to have 2k minus 1 double factorial divided by, okay, and this one is easy. So we are going to have 2, but multiplied with itself 3 times. So 2 to the third power, 2 squared, 2 to the first power, 2 to the 0th power, meaning just 2 to the cave power. And now we are going to compute our cave derivative at x being equal to 0 because we want to get ourselves to Maclaurin series expansion. So meaning, I'm literally shaking right now. What the Whew, holy crap. Okay, the cave derivative at 0 is going to be, we are going to plug 0 into each and every x. Okay, this right here is going to turn into 1 then, and 1 to the something power is just 1. So we are going to be left with the part 2k minus 1 double factorial over 2 to the cave power. Okay, good stuff. Meaning our Maclaurin series expansion is going to be for f of x, hence nothing but the sum, where k is greater or equal to 0, of nothing but 2k minus 1 double factorial divided by k factorial times 2 to the cave power. And also we are going to multiply it by x to the cave power. This is just Maclaurin series expansion. Take a look at my Taylor series playlist. You can find all the explanation there on the series expansions. Now we could have one problem here actually with this definition that we're having here, because what about the 0th derivative? What about our k being equal to 0? Then we are going to get 2 times 0 minus 1 double factorial. This is weird, but it does work. Negative 1 double factorial, I'm going to make a series on double factorials pretty soon. It's going to evaluate to 1 overall. So this representation also holds for the 0th member of our series expansion that we're having. And now we can plug this very series expansion into here with the restriction that we are going to plug our k squared times sin squared of theta into our x to the kth power. Okay, that's what we are going to get. So our complete elliptic integral of the first kind is going to be integral from 0 to pi over 2 of, okay, our d theta can go somewhere here. Also we are going to get an infinity boy, that's an ugly one, I gotta admit it. K being greater or equal to 0 of, okay, k is not a good index to use right here. Let's go with n because we're having a k here. I'm terribly sorry about that. So we're going to have 2n minus 1 double factorial divided by, okay, now we are going to get n factorial times 2 to the nth power, and also x to the kth power is just k squared times sin squared to the kth power, or to the nth power. We can track the n down, leaving us with k to the 2nth power times the sine of 2n of theta. Okay, this is what we are having right now. And now we are going to play physicist and say we can freely interchange under the condition that everything converges, blah, 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 whatsoever. We are going to interchange the infinite series and our integral, as well as bringing the constants to the outside. So k to the 2nth power and also this chunk that we're having here. Meaning the complete elliptic integral of the first kind with respect to k is hence nothing but the series expansion where n, not k, is greater or equal to 0 of 2 times n minus 1 double factorial divided by n factorial 2 to the nth power k to the 2nth power integral from 0 to pi over 2 of the sine of 2n times theta d theta. Okay, now we gotta find out what this integral is, because this right here is the only thing holding us back from getting ourselves to series expansion, am I right? So this right here is actually really easy to solve, because it's actually something that we have derived before. This right here is just a beta function in disguise, which comes in quite handy actually. I'm going to write out the definition for the beta function and we are going to proceed from this point onwards. So our beta function of x comma y has been defined as being gamma of x times gamma of y. You can as always find the link down there in the description, divided by gamma of x plus y. And also by definition this has been the integral from 0 to pi over 2, but 2 times the thing of, and then we had sine of 2x minus 1 of t, and then times the cosine of 2y minus 1 of t integrate with respect to t. And I hope you can see the similarities. What we need to do is we need to bring this integral that we're having here into the form of this integral. So just take a closer look. We need to get something up here in the sign as the exponent of the form 2 times x minus 1, and also we are missing a cosine term. Where's the cosine term? Papa, what are you doing? Well, the cosine term is actually hidden because this is just cosine to the 0th power of theta d theta, meaning we also need to bring the 0th power into the form 2 times y minus 1. And then after we are done with that, we can divide both sides by 2 here on this part, leaving us with some integral of that kind being equal to gamma times gamma over 2 times gamma of x plus y. Okay, so this right here is what we are going to do. We have used this before quite a bunch of times, and now we are just going to go ahead and manipulate our 0 and our 2n into something of the form 2 times blah 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 minus 1. Let us start with 0, which is actually quite easy. So what is 0 exactly? I mean, at first let us get the negative 1 part, okay? Then 0 is nothing but 1 minus 1. I have basically shown this on my second channel already. Flammable Maths 2, subscribe if you haven't done so already. Okay, now we got negative 1, this is good. All we really need is a 2 in front of some factor. Meaning, what is 1? Well, 1 is nothing but 2 over 2, meaning 2 times 1/2 minus 1 is going to be the exponent that we need for our cosine, for example. Okay, good stuff. Now we can go ahead and turn the 2n into something of the form 2x minus 1. Okay, we got the 2 here, but it doesn't help us yet, because we actually need a negative 1 at first. So at first we are going to add and subtract the 1 to this thing. So we are going to add 0. So 2n plus 1 minus 1 is what we are going to have now. I mean, now we got -1, this is good, and all we need to do to get our 2 on here is factor out the 2 on both terms here, leaving us with 2 terms, and then what we are going to get is nothing but n plus 1/2. -1. Okay, this right here is our x, and this right here is going to be our y that we are going to plug into just this definition that we're having here for the beta function. Also, this tiny little part right here is going to be 2n plus 1/2. Okay, this is going to come in quite handy in a second. Okay, now we are going to make use of the beta function here and just plug in the values. Meaning, I'm going to compute this really quick. What we are going to have here is hence nothing but gamma of, okay, what is our x exactly? Our x has been 2n plus 1 over 2 times gamma of, what was gamma? Of what? 1/2, this is good. Okay, we're going to get 1/2 here, divided by gamma of those two arguments added together, so gamma of n plus 1/2, this is n plus 1. Hey, n plus 1, this is actually pretty good. Gamma of n plus 1 is nothing but n factorial. Okay, we're going to get to this in a second, but also times a factor of 2. This is also something that we need. Meaning overall, we can reduce this quite nicely. So this right here is still going to be gamma of 2n plus 1 over 2. Okay, good stuff. Gamma of 1/2, I have shown this before, is going to be nothing but square root of pi. Also, we are going to get the over 2 divided by, and gamma of n plus 1 by definition for natural n, which we have here because it's a summation, is going to be n factorial. Okay, now we got quite some weird stuff going on. We have this double factorial shit going on, and we kind of have now n factorial squared. Also, we got square root of pi, which is absolutely ridiculous, but it's going to reduce quite nicely once we take a look at the half values of gamma, basically. I made a video on that, but like I said before, we are going to derive it from scratch. I'm going to be there in a second. Alright, grande finale. We are going to rewrite now our gamma right here using the half-angle stuff we have already derived before. Now this chalkboard is still quite wet, just like your papa. That's why we are going to continue on this chalkboard for now. So at first I would like to do a few observations on the first few members of this series right here. So what exactly is it at n being equal to 0? Okay, then we are going to get gamma of 1/2. Okay, gamma of 1/2. We just used that, it's going to be square root of pi. Okay, now we are going to take a look at gamma of 3/2, which is going to be the next one in the series. Okay, next member. But 3 is nothing but 2 times 1 plus 1. Okay, so this is gamma of 2 times 1 plus 1/2. Okay, now what is gamma of 3/2? By the recursive definition of the gamma function, this is going to give us this argument reduced by 1 times gamma of the argument reduced by 1. Meaning this right here is nothing but 1/2 times gamma of 1/2 actually. And 1/2 gamma of 1/2 is going to give us, well, square root of pi over 2. Now we can start going further. What exactly is gamma of 5/2? Well, by the definition of our n that we're having up here, so the numerator, we are going to get gamma of 2 times 2 plus 1/2. But this right here by the recursive definition of the gamma function is nothing but, okay, argument reduced by 1 is going to be 3/2 times gamma of 3/2. But we know what gamma of 3/2 is. This is exactly square root of pi over 2. Meaning this is going to give us 1 times 3 divided by 2 squared times square root of pi. Hey, this is taking shape, this is good. Okay, let us go for one more iteration, shall we? No, we don't even need this actually. Yeah, let us go for one more iteration. So we know the process by now. Gamma of 7/2 is going to be gamma of 2 times 3 plus 1/2, which is going to be 5/2 times gamma of 5/2, which is going to be 1 times 3 times 5 divided by 2 to the 3rd power. Okay, just plugging this in, times the square root of pi. So what exactly is gamma of 2n plus 1/2 then exactly? Let us formalize this a bit more, and you might notice that the double factorial is going to pop up yet again. So if we have gamma of 2n plus 1/2, it's going to result in, okay, let us take a look. Our n right here for this part was 3. How can we get 7 out? Oh no, not 7. How can we get 5 out once again? This is the same situation that we had before. Third derivative gave us 2k or 2 times 3 minus 1 double factorial. Meaning in the process we are also going to get, if our n is equal to 3, here we are going to get 2n minus 1 double factorial divided by, okay, 2 to the third power, 2 squared. Once again, pretty easy. This is just 2 to the nth power. And also we are going to get square root of power out. Okay, this is kind of fancy if you ask me, because, well, we are basically just going to get this part that we're having here once again. So meaning, if we were to plug our new definition for our gamma of 2n plus 1 over 2n, we're going to get the infinity boy, where n is greater or equal to 0 of. Now, what are we going to have? I mean, we are going to have square root of par times square root of par is nothing but par over 2. Let us bring this to the front actually, giving us par over 2 times what we have here, the summation. Okay, we are going to get, and this has been n, not k, we're going to get 2n minus 1 double factorial squared. Also we are going to get 1 over 2n times 1 over 2n is 1 over 2n squared. Also we are having n factorial squared, meaning overall we are going to have a big clusterfuck right here. This is 2n minus 1 double factorial divided by 2 to the nth power times n factorial, but the whole thing squared. Hey, this is pretty cool if you ask me. So everything we got is just squared, and maybe now you might know why I think this is one of the coolest series expansions, because it's just cool to look at if you ask me. And also we are going to have obviously k to the 2nth power. For sure you can bring the k to the nth power into here too if you wish. Now I would like to write this out a tiny little bit such that you get a feel for the series expansion. We are basically done, by the way. I just would like to rewrite this denominator a tiny little bit more. For this we are just going to write it out a tiny little bit. So what about 2 to the nth power times n factorial? What about n being equal to 0? So for n being equal to 0, we are going to get 2 to the 0th power times 0 factorial is going to be 1. Now what about n being equal to 1? Okay, n being equal to 1 is 2 times 1 factorial, which is 1, giving us 2. Okay, next up, what about n being equal to 2? N being equal to 2, we're going to get 2 squared, so 2 times 2 times 2 factorial is going to be 1 times 2. Hey, this is nothing but 2 times 4. Maybe you are going to notice something. Let us do one more iteration. What about n to the third power? I mean, we're going to get 2 times 2 times 2, and we are going to get 3 factorial, which is 1 times 2 times 3. And by definition, what we are going to have now is, okay, in a second, so this right here is going to result in 2 times 4 times 6. By definition, what we are having here is nothing but 2 times n double factorial. This just holds by definition. So meaning this 2n times n factorial is 2 times n, but the double factorial of this thing. I mean, I hope you can see this. This is just 6 double factorial, 4 double factorial, 2 double factorial, and 0 double factorial that we're having. I think this should be 0. No, 1 double factorial, but really doesn't matter in this context. Meaning, we can actually rewrite the series expansion a bit more into 2 times n double factorial. Yeah, and this right here is the full-fledged series expansion for the complete elliptic integral of the first kind. Wasn't even half bad, right? I mean, it was just some elementary operations that you can do, I don't know, in your first semester of university actually. Let us write it out a tiny little bit. I would like to write out a few terms. So what are we going to get? We are going to get pi over 2 times. Okay, what is the first one? I mean, we are going to get, if this is 0, negative 1 double factorial is 1. I said this before, and 0 double factorial is also 1. So we are going to get 1, and then k to the 0th power, which is 1 overall. So the first term is 1 plus. So our k part on n being equal to 1 is going to be k squared. Now what about if we plug 1 into here? I mean, this is going to give us 0 double factorial, this is 1, and then 2 double factorial, which is going to be 1/2. Now next one is positive, and we are going to get k to the 4th power. And what are we going to get here? I mean, this right here is going to give us, at n being equal to 2, 3 double factorial, so this is 1 times 3. Divided by, okay, this is going to give us 4 double factorial, which is nothing but 2 times 4. Okay, and so on. And the next one is going to be, okay, we are going to get k to the 6th power, 1 times 3 times 5, divided by 2 times 4 times 6. and so on. And this is our complete elliptic integral of the first kind, and actually you can cut it off really nicely if you cut all those off, meaning our initial angle, our initial displacement was really small, hence the sine is also extremely small, and if you raise it to some powers it's going to be even smaller, very near to zero, then you're going to just get your period time basically really easy out. So if you use the formula from less time for the small angle approximation. And yeah, this basically concludes it. Like I said before, I would like to create a little Python implementation for the complete elliptic integral of the first kind pretty soon. And yeah, up until then, thank you guys for watching. Don't forget to check out today's sponsor, The Reg. They were kind enough to sponsor this video. And yeah, don't forget to check out Flammable too, blah blah blah, and all the prerequisites video. Until next video, I wish you guys Flammable day. Ciao.